All right, so we're looking at two variable data, lines of best fit and correlation. Okay, and as I said, a lot of it is common sense. Okay, so don't think that it's hard, it's a lot of it's common sense. So we're learning what a scatter plot is and what information you can learn from one. And we're learning about trends in data. Phones off. Josh, phones off, pencil, highlighter. All right, so a scatter plot is a graph that shows the relationship. Oops. What happened there? The relationship between two variables. The points in a scatter plot often, not always, they often show a pattern, or we call it a trend. From the pattern or trend, you can describe the relationship. Okay, so, and we'll give you the words that you're going to use to describe it mathematically. Okay. So here's our first example. Julie gathered information about her age and height from the markings on her wall in her house. So you can see she's got her age, and since it's first, we're assuming it's going to be on the x-axis. We'll check that out. And then the second column, even though it's horizontal, it's her height in centimeters. Let's make sure that is what happened. Yep, so this is our x-axis, and this is our y-axis. So we can see she doesn't have anything for 0, but when she was 1 year old, she was 70 centimeters. 2 years old, looks like 81 or 82. Everybody good? Okay. So label the vertical axis. So it's y, but it's also her height. And it's measured in centimeters. And the horizontal axis was already labeled age in years. And you can see the graph has that title, that y versus x title, Julie's height versus age, y versus x. So whenever they give you a title for a scatter plot, the first thing they tell you is what's going to be on the vertical axis versus what's on the horizontal axis. Okay? All right, so now we're going to get into some terminology here. Describe the trend in the data. So if you were just looking at this, what's the trend? We'll look at as many ways you can describe it as possible. Yep.
It's non-linear. Is that like what you mean?
No.
Ah.
But that's if we were just to join the points, it looks non-linear, doesn't it? Yep. So we're going to talk about line of best fit today. So that's a good observation. The trend, so overall the trend is, so when you're looking for a trend, what you want to do is look at what happens to the y values as x gets bigger. So as her age gets bigger, what's happening to the y values as an overall trend? And think about it as she gets older, what's happening to her height? Yes. Okay, so as she gets older, she gets taller. We also call that a positive or increasing trend in the data. Because if we were to draw in a line, Alexa, like just a line of best fit, which don't draw that in because we're going to talk about how to draw one, but if I were just to draw a line, that line would have a positive slope. Does everyone agree? Okay, so that's how we're saying positive. And increasing, so as age gets bigger, her height's getting bigger. Okay? And anything else you could say to describe the trend in the data? Those are great, both of them. Describe the relationship. We already did that. Oops, undo. So this is a great description of the relationship right there. As she gets older, she gets taller. Okay, so does it seem very commonsensical so far? Okay. Variables. So the dependent variable is always located on the y-axis. This variable depends on the other variable. So dependent variable is always the y, okay? Independent variable is always on the x-axis. And this variable does not depend on the other one. So if we look back at Julie's example, which variable was dependent? Yep, her height. Her height was dependent on what? Her age, which is the independent. So height depends on age. Okay, height depends on age. And then you can see this, we've done it so many times, but good to note, by convention, the independent variable always comes first in the table of values. Also by convention, it's always on the horizontal axis. Horizontal is independent. And vertical is always dependent. So independent always comes first in the table. So if you get like an EQAO question that gives you a table of values and it says what's the independent variable, it's the one in the first column. So age in this question, right? And if they ask you what's the dependent variable, height in this question, the second column of the table. All right, so the line of best fit. To be able to make predictions, I need to model the data with a straight line or a curve of best fit. Okay, so here are the rules for drawing a line of best fit, because in this grade, we focus mostly on lines, okay, as evidenced by how long unit 4 has to do. So the line must follow the trend. Okay, the line has to follow the trend. So these are the rules for drawing the line of best fit. The line should pass through as many points as possible, although sometimes it's not possible based on the other things that we have to take into consideration. There should be an equal number of points above and below the line. There should be an equal number of points above and below your line. So it's going through kind of the middle of the data, okay? And the line should pass through points all along the line, not just at one end, okay? So you're thinking of the whole data, not just the part you think looks like the most linear part of it, okay? You have to take into account all the data points. Unless there's an outlier, and we will see a question where there is an outlier. This looks like we got some at the door. Thank you. All right. So let's look back at Julie then. And I'm going to erase my line of best fit, and we're going to draw one in together. Okay, so everyone's going to get their ruler out. And we have these rules. It has to follow the trend of the data. So the line you draw has to have a positive slope. It's got to go through as many data points as you can, and it has to have an equal number on one side and the other. it has to take into account all the points, not just part of them. Like here, maybe that's the part that looks most linear. You can't just focus on those. You have to focus on the whole thing. So you guys, grade 9s, try to draw on a line of best fit, and your partners will tell you how good yours is. I'm just gonna freehand run here, see how good mine is. Okay, there's mine. Another one we just put on there is that we want to minimize the distance between the points we don't go through and the line. Okay? Minimize the distance between the points we don't go through and the line. Did you draw your line of best fit in?
No.
And then have time to look at it? So we don't just join the points, it's not like a weather graph or something, and you don't just redo it, you use your ruler, you knock about with it, and try to find your line of best fit. Okay?
Got it.
Everyone think they've caught on what the line of best fit should look like for this one? Okay. All right, so now we're going to look at the graphs below and explain what's wrong with the line of best fit shown. All right, so if we look at the first graph number 1. As soon as we're done this lesson, it's not that long. Can you tell me what's wrong with the line of best fit? It looks pretty good, but what do you think's wrong with it? In the first case.
It's not touching any dots.
It's not touching any dots. Okay, can someone name another thing that's wrong with it? Yep.
It's like not touching any of the other lines. It's better than not.
Like down here, you mean?
Yeah, it's starting anywhere.
Yeah, I could agree with that. Anything else you notice?
No.
Anyone else think they see something that they would draw a bit differently? It was kind of the big one that I didn't say, but you want to minimize the distance between the points. So would you say that this line's skewed to the lower points a bit more and not taking into account the points that are a bit higher? So if I drew this one in, it's pretty good as I said, but I would probably do what Paul said and start here. And then I would try to go through some data points and minimize the distance. So it would kind of look something more like that, where these two are just as far apart. And I don't know, that would probably be a bit better. How about number 2? That should be an easy one. What's wrong with that? It does not follow the trend of the data, okay? So if we drew this one in, we want it to follow the trend of the data to have a negative slope, not a positive slope. That was an easy one. Follow the trend of the data here. What's wrong with the third one? It's not a straight line. Okay, they did like the weather model where you just join the points, so they need to draw in a straight line. Should have a negative slope again. Something like that would be better. Okay. Shows the trend of the data, has an equal number of points on each side, goes through some of them. Okay. What's wrong with this one? Yeah, there's not an equal number on each side. It's way skewed towards the bottom. So it should go through the middle of the data, right? The middle of the data, if you want to think of it like that. So that one's much better. Goes through the middle. What's wrong with the next one? What's wrong with 5? Yeah, it only talks about these ones, it doesn't, it says kind of, let's not do those, okay? So how can we, it shouldn't be a steep, does everyone agree with that?
Yeah.
This one, really for me, I would draw in a curve of best fit, like I would do something like this. And draw in a curve of best fit. Because this one, sometimes, like it's just so obvious that it's a curve. But if I was forced, if they said you have to draw in a line of best fit, I guess I would try my best. So something more, it would have to have a less steep slope for sure, right? And same number of points on each side, ish, okay? I was forced to, but I would say no, that looks more like a curve to me. And this one they have drawn in a curve of best fit, which is it should be. So what's wrong with this one? It should be a curve of best fit, but what's wrong with it? According to our rules, it only takes into account this part of the graph. So it should take into account the whole thing. Okay? Nice. All right, so again, a lot of really common sense things. Interpolate, when you interpolate, you're making a prediction within or inside the data. So those words are kind of new for us, so I would think interpolate and inside the data. Interpolate, you're making a prediction inside the data. These predictions are usually accurate. So if you're given a big data sample and you're trying to find something in the middle, it's usually pretty accurate. Extrapolate. So the word extra is an extrapolate. You're making a prediction outside the data, like you're adding on an extra part to the line. Adding an extra part to the line. And it often requires you to extend the line. Extrapolate, extend. Extrapolate, extend. So here we have Julie again. Oh, and sorry, these predictions are less reliable. So when you have to extend the line, the predictions become less reliable because you don't have any data for that. And just like age versus height, if I just drew in a line of best fit and used it to predict how tall I would be at 80, I'm not going to be like way, way, way taller, am I?
Yes.
No. When do you stop growing-ish? 18 to 21, depending on genetics and stuff. Okay? So this isn't going to be reliable. At 80, you're not going to be like, you're not going to still be following that slope. That just wouldn't make sense. Okay? So that's why when you extend the line, your predictions are less reliable. When you're just finding within, they're way more reliable. Okay, so all right, so making predictions. How tall was Julie when she was 5 years old? So let's draw in our line of best fit again, and we're going to use it to make some predictions. And yours will be a little bit different from mine. Everyone's is going to be a little bit different, but the same general line. Okay, there's mine. And it's a little bit different than the one I drew on the first page. Josh, draw it in. good? Okay, let's look at the first one. How tall was Julie when she was 5 years old? So what I would do is I would take my ruler and I would go up to the graph, to the line, not the graph, at 5, and then read across with my ruler. So it looks like it's like 112-ish, okay? (112 centimeters), and the method of prediction was interpolate. Yep. Sorry, what did I do?
It's under 10. Oh, no.
Everyone's got a different one. Line of best fit. So just as long as you do what yours said. Oh, that's, I'm glad you said that. Okay, so if you're looking at this data point, that's another thing too. So according to her data, we could even look way back at the chart and see how old she was at 5, or how tall she was at 5 years old. It was 106, right? But we're using our line of best fit to predict instead of using her data points, okay? So she was actually 106. This is just a prediction, estimate, prediction, okay? So you're right, Kylie. She was only 106 centimeters tall, but according to my line of best fit, it looks like she was about 112, okay? So obviously the prediction is less reliable than the table of values, right? But it's more reliable than if I extended the line. So since I'm finding it within the data, it's fairly close to what she actually was. Okay? All right, so again, how tall will Julie be when she is 9 years old? Now notice 9 is outside of the data, so this one's going to be less accurate. So I'm going to draw in my line at 9 years old. Up to the graph. Oh, it's right on the corner for me. I'm predicting 150 centimeters if her growth rate continued at the same rate. How tall will she be when she's 9 years old? So you see how I drew up to with my ruler, up to the line of best fit, looked across, and I saw 150 centimeters based on my line of best fit. Okay? 150 centimeters, and this time we had to extend the line, so it's called extrapolate. Okay, when was Julie 100 centimeters tall? So again, this is a prediction, so we use our line of best fit. So I'm going to use, I don't know, purple and a line. And now at this time I'm going across to my line to 100 till it hits my red line. Oops. And then I'm going down to see how old she was. So like more like close to 4, so we could say three and what do you say? 3 and so many months? 3 and almost 4. That's a good one, almost 4. So almost 4, and that was within the data, so it was an interpolate one. We didn't have to extend the line to see it. And then how tall was Julie when she was born? How tall was Julie when she was born? So that's going to be where our line started, right? Everyone's line starts a little bit differently, so I'm going to use highlighter for this. So it looks like she was 62 centimeters from my graph. Everyone's will be different, but this is where I'm looking, the y-intercept. So that's like 2 rulers, 2 of your rulers and a little bit, okay? And did we have to extend the line with outside the data points? Yes, we did, because remember it started at 1 and we had to go back to 0. So this is an extrapolate again. Because we had to extend the line in the other direction to figure it out. So that's how you use a graph to make predictions. Okay, and then oops. We're talking about correlation now. So here's a new word for you, correlation. It's a statistical technique that can show whether and how strongly, whether or not, and then how strongly pairs of variables are related. So types of correlation, when one variable increases as the other increases, we say the correlation is positive, just like Julie, right? When one variable increases, so when her age increases, her height increases, we say the correlation is positive. Okay? And we can think about Julie here. As her age increases, her height increases. Okay, that's called a positive correlation. So it's really easy for us. If there's a positive slope, it's a positive correlation. If it's a negative slope, it's a negative correlation. Okay? All right, so then here's what we call a strong positive correlation. Can someone tell me the difference between a strong positive correlation and a weak positive correlation? Jacob.
The strong positive correlation, so then the dots are more together.
Yes. Okay, so that really looks like it's forming a line. Like you're really convinced that it's a line of best fit and that the data matches, right? So this is strong positive. Weak positive, there's still a correlation. As this gets bigger, so is this, but not so tightly in the same trend, right? So that's a weak positive correlation. Here's a strong negative one. Remember negative slope? Give me an example of something in real life, 2 things that would relate, that would have a strong negative correlation. 2 things in the real world that would relate, that would have a strong negative correlation. So as something increases, the other one's decreasing. Something in real life. Can be anything. Here's one. So number of items in grocery cart, amount of money in checking accounts. That's true, right? What about the distance you drive and the amount of gas in your car? Yeah? So the farther you drive, the less gas there's going to be in the car? Yeah? Anyone think of any other ones? Those 2 make sense? Okay, a weak negative correlation. All right, just not as tight around the line of best fit, but still showing a negative trend. Moderate negative correlation. Why is this one stronger than this one? Why is this one stronger than that one? Yep. Way more dots. So if I superimpose this over here, there's just way more data points to rely on. So it's stronger evidence that that is a line of best fit. Okay? Nice. Now, if they were even tighter together, then it would become strong, negative. Okay? They were even tighter together. And no correlation. So why does this one have no correlation? Right, so if I'm thinking as this gets bigger, what's happening here? Could I predict with any kind of success what's happening here as X gets bigger? No. Sometimes it's getting bigger, sometimes it's getting smaller, sometimes it's in the middle. There's no correlation between them. Okay? And there's lots of things in life that have no correlation, right? Like, I don't know, the number of kids that come to class and...
Well, that's a small number.
Pardon?
That's a small number of students.
I'm just saying, and what it would have no correlation? The number of kids that come to class and, I don't know, the price of groceries. That has nothing to do with each other, right? So we have no correlation. All right, so we're going to do this Desmos polygraph correlation. I haven't loaded it yet, so I'm going to load that right now. Yep, so get your laptops ready.